Alright, so now that you've gotten a chance to look at this one, let's go ahead and try to tackle this here. Remember the volume of a cross-sectional slice is the area of that cross-section times the thickness. Remember the thickness is what we're going to use as either the dx or the dy. Okay? Now a couple of details we need to pick out here. First of all, the base of the solid is given by x squared plus y squared equals 4. So what we need to do really here, since that's a circle, we actually need to define an f of x and a g of x, so to speak, for our upper and lower functions that define that circle. Okay, so what I'm going to do is I'm going to rewrite this as y squared equals 4 minus x squared. And then the upper half of this circle is going to be y equals the square root of 4 minus x squared.
So just 2 minus x.
And the lower, no, subtraction there.
Oh, okay.
And then the lower half is going to be the negative square root of 4 minus x squared. Okay? So, I'll make this one red. Alright, this bottom half is this part here, this semicircle, and the top half is this. Okay? So, now that we can see that, let's look at what this cross section is. It says it's a square. Each slice is a square. Okay? In other words, this and this are the same, even if they don't look like it. Okay? So if this was the positive, and actually let's go ahead and call that f just for ease here. There's our f of x, and we'll call this our g of x. And g of x is right here. And the f of x is right here. So, if we're looking at this square, this side right here, or each side of the square, is going to be f of x minus g of x. Okay? F of x minus g of x. So that means that the area of this square is obviously side squared, so that's f of x minus g of x squared. Okay? So now we're going to be able to set up our integral, okay? You guys know this is going to be dx, the width or the thickness of this slice. All right, so what's going to be the integral that we're going to use to find the volume of this object?
Would it be 2 negative 2?
Okay, good. We had to figure out the intersection points, so which are just the edges of this circle. So that's going to go from negative 2 to positive 2. Because this equals 4, the radius is 2. Okay, so yeah, we're going to take the integral from negative 2 to 2 of that square dx. Okay, so you have the f of x minus g of x squared. So now we have to actually just put that in there, the f of x and the g of x. Okay?
Yeah.
Are there any questions up to this point?
How come you subtract f of x minus g of x?
Well, because you got to get the distance. To get the distance between two y values, you subtract them.
Oh.
Alright, so now plugging in the actual functions, v is the integral from negative 2 to 2. f of x is the square root of 4 minus x squared minus g of x. Well, g of x is a negative square root of 4 minus x squared. And I'm going to square this whole thing. Before we get too far, let's go ahead and simplify. I have square root of 4 minus x squared plus square root of 4 minus x squared. So that's just 2 square root of 4 minus x squared that I now have to square. Okay? Simplify first. Please don't FOIL that all out. Okay? Now we square it, and we get 4 times 4 minus x squared.
Oh yeah, I did it a different way, but I got to that same part.
You got there eventually?
Yeah.
That works. That's what's cool about math. You can get the same place a bunch of different ways.
That's true.
So, all right, so now we distribute, and then we can finally take the integral here. So we have 16x minus 4x cubed over 3 evaluated from negative 2 to 2. So v, if I plug in a 2, I get 32 minus 32 over 3 minus, if I plug in a negative 2, I get a negative 32 and a plus 32 over 3. Okay, so I got 32 plus 32 is 64. Negative 32 thirds minus 32 thirds is a negative 64 thirds. Okay, 64 is 192 thirds.
That was really fast.
Minus 64 thirds.
128.
128?
Maybe.
Yeah, that looks good.
Oh, yes.
128 thirds. Or 42 and 2 thirds.
A lot of personal pride writing on that one.
Good.
I matter.
Alright. Now, either one of these is fine.
It's just 64 times 2.
Oops.
Wow. I actually did 192 minus 64. It's just 64 times 2.
Yeah, it is. It works. Okay, does that make sense? Okay. Alright, let's go ahead and take a look at this one. Again, it tells us that it's perpendicular to the y-axis, so we need to have everything as functions of y, because we're going to integrate with respect to y. Alright, now, since we're given that x squared is 8y, again, we're going to have... Thanks. Again, we're going to have to rewrite this as x equals a positive square root of 8y, which is 2 root 2y, and also x equals a negative 2 root 2y. Okay? And the line y equals 4. Now, what that gives us, the reason why they gave us that is because these only intersect at the origin. Okay? So, I'm going to be integrating from 0 to 4. Alright? Now, we need to think about which one of these is greater, and obviously the positive one's going to be greater than the negative one, since everything else is the same. So, I've got an equilateral triangle. Alright, I've got an equilateral triangle. So let me draw this equilateral triangle here for you. You may remember the formula for an equilateral triangle from the one that we did the other day. Okay, but if this is, we'll call this the f of y, and we'll call this the g of y, then the side of this equilateral triangle is going to be f of y minus g of y. Okay? Now, you may recall, because we have an equilateral triangle, okay, this height is going to be half of the side times radical 3, because we have a 30, 60, 90 right triangle and we drop that height down. Okay, so the height is going to be half of the side times radical 3. Alright, so in this case, that's root 3 over 2 times f of x minus g of x. Sorry, y. F of y minus g of y. Okay?
Does it S over 2?
S over 2, yeah, the side of the equilateral triangle.
Oh.
Alright, so side, this is going to be side over 2, side over 2, okay? And you've got a 60-degree angle here, you got a 30-degree angle here, because it was cut in half, 60 was cut in half,
Yeah, makes sense.
okay? Alright, so now when we're integrating here, we're going to take the integral from 0 to 4, oh, I already started writing that one, the integral from 0 to 4 of the area of this triangle. Well, the area is 1/2 base times height, okay? So it's 1/2 times the base, which is s, times the height, which is root 3 over 2 times s. Okay? So in other words, the area is root 3 over 4 s squared. And we already know that s is f of y minus g of y. Okay? So the area here is root 3 over 4 f of y minus g of y squared. Okay? Well, f of y is 2 root 2y. 2 root 2y. G of y is a negative 2 root 2y. So we're just going to be adding it. Yep. So here we have root 3 over 4. Okay, so that's root 3 over 4 times 4 root 2y. And now we're going to square that. Okay, now we're going to square that. By the way, notice I'm just simplifying my area before I even stick it into the integral. Okay, that may help you. It's less writing for one, but it may help you just keep things neater and organized. Okay? So now when I square this, I have root 3 over 4 times 16 times 2y. So that's going to be 8 root 3 times y. Okay? 8 root 3 times y. Does everyone understand that? This is actually a pretty easy integral to do now that I've gotten all that done. Okay, so we're going to integrate from 0 to 4 the 8 root 3 times the y dy. I'm going to pull the 8 root 3 out. So we're finding volume now. And that's going to be the integral from 0 to 4 of y dy. So of course that's y squared over 2, evaluated from 0 to 4, and then multiplied by the 8 root 3 at the end. Okay? So if I plug in 4, I get 16 over 2, that's 8. If I plug in 0, I get 0. Okay? So the volume is simply a 64 root 3. Okay, which is choice B. Okay? Any questions about this one? Yeah, these are hard because they're hard to picture. So, you know, if I have from in perspective here, you know, the y-axis and the x-axis, you know, I've got this parabola. I've got this parabola here, and I've got the line y equals 4. Okay? And essentially what I've got is this like shape. Oh wait, sorry, that's equilateral triangles. So it kind of comes up to this peak, and there's an equilateral triangle there, and that's a terrible drawing. Okay? But it's really hard to kind of see. But that's what makes these the hardest, is it's hard to visualize. But once you get the hang of, I just gotta get the area of the cross section, take the integral, and I'm good to go. They're really not too bad. So let's go ahead and work through this one now that you've had a chance to see it. All right, so first of all, we have the shaded region enclosed by y equals tangent squared and y equals 1/2 secant squared. If we plug in 0, tangent squared is 0, so this bottom is the tangent squared. Okay, I'm going to go ahead and call that the g of x, since in a lot of our formulas the bottom one was g of x. And I'm going to go ahead and the top one was the 1/2 secant squared. Okay, now identifying some points here might be helpful. Right. But we'll call this one f of x. Alright, so you've got 0, 0. With secant, if it's 1/2 secant squared, what do I get when I plug in 0? No? A half, yeah. That's alright. So we have 0, 1/2 here. Now we also need to figure out what is this intersection point here. So I'm going to set up an equation. Tan squared is 1/2 secant squared. There's a bunch of different ways that you could solve this. What I would do personally is make it all in terms of sines and cosines. You could also make the secant squared into a 1 plus tangent squared if you want. It's totally up to you. This would be 1 over 2 cosine squared. Alright? Or, to make my equation a little easier to solve, I'm going to go ahead and just leave the 1/2 in the numerator, because then my denominators will be the same. And if the denominators are same and the fractions are equal, then the numerators must be equal. So sine squared has to equal 1/2. Okay? You square root it. Sine of x is plus or minus root 2 over 2. Okay? Now, I know this is positive. Alright, so I know my sign has to be positive, so I can just ignore that negative. Where is sine root 2 over 2? At pi over 4. Alright, so this is the first intersection past the x-axis, so I know it's got to be this pi over 4 here. Okay? So that right there, pi over 4. Okay? Questions so far? Alright, so now, just finding the area between, you're simply taking the integral of the top minus the bottom. Okay? So integral of the top minus the bottom. So in this case, we've got the area is going to equal the integral from 0 to pi over 4 of tangent squared x minus a 1/2 secant squared. Now, do we know the integral of secant squared? Oh, wait, yeah. We already said that. That's the top right here. Thank you. Oh, I hate it when it does that. Okay, let's try that again. Okay, so we've got the 1/2 secant squared minus the tangent squared. Now, do we know the integral of secant squared?
Yeah, tangent.
Yeah, it's tangent. That's nice. Do we know the integral of tangent squared?
Secant tangent.
Well, the integral of secant tangent would be secant. We don't really know the integral of tangent squared though. But what could we do with this?
Straight 2 sine cos 1.
I could.
Cotangent?
Even easier way. Think about Pythagorean identity. What does tangent squared equal?
1 plus
One.
1 secant squared minus 1.
Secant squared minus 1. There we go. Alright, so we're a little rusty on that. So 0 to pi over 4 of 1/2 secant squared x minus secant squared x minus 1. Alright, so good, we have 1 minus, or a half minus 1, so it's negative 1/2 secant squared plus 1. Now I have something I know how to take the integral of, from 0 to pi over 4. Okay, so the area is now negative 1/2 tangent of x plus x evaluated from 0 to pi over 4. Here's a good example of don't just assume that when you plug in 0 it's going to equal 0, even though in this case it does. Alright, please don't just assume that when you have trig. Okay, but that means our area is going to equal negative 1/2 tangent of pi over 4 plus pi over 4 minus, and tangent of 0 is 0, plus 0 is 0. Okay. What's tangent of pi over 4? 1. So this is a negative 1/2 plus pi over 4. And you'll just leave it like that. Okay? You're just going to leave it like that. Now, part B, we're asked to set up but do not integrate an integral expression in terms of a single variable for the volume of the solid formed by revolving region R about the x-axis. So what do you have here? We could just write it down at this point. Pi
Times the integral from 0 to pi over 4 of secant squared of x over 2 minus tangent squared of x all squared. So I guess you could distribute this squared.
We have this over 2 minus tangent squared,
And that's all squared.
and this is all squared dx. Now let's see, it says in terms of a single variable. Do we have just a single variable? Yes. It doesn't say we have to have it all in in terms of one trig function, so we're done. Okay? And no, there's not a good way of doing this one by hand, so this is why they said don't bother doing it, because this is a no calculator problem. Oh yeah. Hang on, guys. Thank you, Arthur. I'm mixing ideas. We should be squaring these separately. Thank you for speaking up. I got caught in the cross-section mode from yesterday where we subtracted first then squared. Okay, here, yeah, because remember what we're doing is we could do pi times the integral of the upper squared minus pi times the integral of the lower function squared.
Where are you writing? It's not showing up.
Right there. Sorry. Froze the screen. Yeah. Yeah, so each one is squared individually. We have an expression you don't have to simplify. Okay? If you wanted to make it secant to the fourth over 4 minus tangent to the fourth, you can, but since we're not evaluating it or integrating, then we could just stop there because we got what we were looking for.
Do you always have to square it separately?
When doing the area between and finding the volume, yes. Yeah. All right, let's go ahead and take a quick look at this one, okay? Let R be the region enclosed by the graphs of y equals 64x to the 1/4 power. Okay, so this is going to look.
It's you close the screen.
Something like this. Okay, and then you have the line y equals x. Well, the line y equals x is like this. Okay? So, we have here intersection points, and they're actually at 0 and something. Okay? 0 and 4. Alright? Now, just to confirm, if we were doing this, we would do, we have the fourth root of 64x equals x. I'd have to raise everything to the fourth power. So I'd have a 64x equals x to the fourth. I subtract, and I can factor out an x, so it's x times x cubed minus 64, which I can factor using difference of cubes. I have x times x minus 4 times x squared plus 4x plus 16. Okay? X squared plus 4x plus 16 does not have any real roots, so therefore my answers are just 0 and 4. Okay? Now, which one of these is on top? Plug in something between 0 and 4, like something easy, like 1, and see what you get. Right? If I plug in 1, the 64 times 1 is 64. The fourth root of that is bigger than 1. Okay? I don't know what that is, but it's bigger than 1. So I know that that's going to be my top one. Also, if I know how to draw it, I know that that's what's happening too. Okay? So, here the integral. I'm taking the integral for my area from 0 to 4 of that fourth root of 64x minus x dx. Okay? You can use the power rule for that. Just make it the fourth root of 64 times x to the 1/4, and then use the power rule. What did you guys get for the integral, though, once you finished?
I mean, this one.
Yeah.
This one is for.
I can't remember.
It
Huh?
says revolve about the x-axis, so it should be volume.
Oh, yeah, it's volume. Okay, sorry. Yeah, that's area. Sorry, this problem is a little different. So if we're revolving this around the x-axis, that would be our area. The volume, we would take that area, spin it around. So that's going to be pi times the integral from 0 to 4 of that 4th root of 64x squared minus x squared. Okay? Which you can simplify. V equals pi times the integral from 0 to 4. That's going to make that 4th root into a square root when I square it. So the square root of 64 is 8. So it's 8 radical x minus x squared dx. So what'd you get for that? 64 pi over 3?
I got
Okay, so that's the work on the right for the integral, if you want to take a look at that. But we got 64 pi over 3. Now it says, set up but do not integrate an integral expression in terms of a single variable for the volume of the solid generated when R is revolved about the y-axis. Okay, so this one's a little bit different. We got to rewrite that 64x to the 1/4 in terms of y instead. And notice we're doing right minus left, so the line is going to be to the right in this case. Okay? So we're going to do, we are going to do the integral with respect to y. I am revolving it around, so I am going to have something squared minus something squared. Okay? Notice here, though, we need to use y coordinates for our boundaries. Well, this one is still at 0 on the bottom, but this was the point for what? It actually is 4, 4. Okay? But I want you to make sure you understand these are y coordinates just because they happen to be the same. That was nice, but these are y coordinates. So now, again, you always do the one that's further away from the y-axis minus the one closer to the y-axis. So the line x equals y is further away. How would you rewrite this 64x to the 1/4 power in terms of y? Good. Y to the 4th power divided by 64. X equals y to the 4th over 64. Okay? So y to the 4th over 64. If you want to simplify, and I have to have a pi too, I almost forgot. Got a pi. So, if you want to simplify a little bit, you can. Integral from 0 to 4. That's going to be y squared minus y to the 8th over 64 squared, which is 60 times 68, 3,600, 4,080, 4,096. Is that right? Someone help me out.
Terry.
Is 64 squared 4096?
I think we do not integrate.
4096. Yeah, that's right.
I think we just need to set up.
That's right. We're not going to integrate right now. We're just setting it up. Okay? So that was all they were asking us to do on that one. All right, so let's tackle these last two problems here. All right, so this 1988 AB3. We're going to let R be the region in the first quadrant enclosed by the hyperbola x squared minus y squared equals 9, the x-axis, and the line x equals 5. All right, so let's give ourselves a little sketch here. The hyperbola x squared minus y squared equals 9 is centered at the origin. What we realize is this actually has a horizontal axis, and what it looks like is this, all right? And there's an asymptote here and an asymptote here. You might remember this back from days of studying conics. All right, so we've got this part over here. Now, we only want the part in the first quadrant. And what we just discovered here is that this is going to hit the x-axis at 3 and also -3 over here, but 3 is the part that we really want. And then we have the line x equals 5, so 4, 5. So the area R that we're actually talking about is going to be this area right here. Looks like it's going to be pretty cool once we spin this around here. Okay? So initially you might be thinking, wait, a hyperbola looks a certain way, but this hyperbola is a little bit different. It's a horizontal one. It's from our conics. And one of the things that we also need to look at here is notice that it's given in that conic form, x squared minus y squared. If I solve it for y, however, I'm going to get x squared minus 9 square rooted equals y. Now it's plus or minus, all right, but I'm just going to use the plus side of this because it's above the x-axis here. All right, so now we've got to find the volume of the solid generated by revolving R around the x-axis. So volume of a solid, here there's no upper or lower function, which is kind of nice. So it's just V equals pi times the integral from 3 to 5 of that square root of x squared minus 9 all squared dx. Okay? So there's our pi r squared that we're taking the integral of. All right, so the integral, or the square will undo the radical. So that's pi times the integral from 3 to 5 of just x squared minus 9. So now we're to the easy part. Just take the integral, evaluate it, and we are done. Okay? So let's do that. Our volume is pi times x cubed over 3 minus 9x evaluated from 3 to 5. Okay. If I plug in 5, I'm going to get 125 over 3 minus 45 minus, when I plug in 3, I get 9 minus 27. I'm going to multiply all this by pi. Okay, so when I simplify all of this, I get 41 2/3 minus 45, so it's a -3 1/3 plus 18, so that's going to be 14 2/3 pi. Okay, so that is the volume of that solid. All right, now part B says set up but do not integrate an integral expression in terms of a single variable for the volume of the solid generated when R is revolved about the line x equals -1. Okay, so here notice first of all we're going to have to go with a horizontal integration with respect to y because we're revolving it around a vertical line. So here's -1. Okay, so the first thing I'm going to do, I'm going to write everything in as a function of y this time. So notice y equals the square root of, or I'm sorry, x equals the square root of x squared minus 9. X equals the square root of, y squared minus 9. And then because I'm revolving it around the line x equals -1, I actually need to shift everything to the right 1 unit. Okay? So I'm going to shift that over, and I'm going to shift this over 1 unit. Okay? So that means I'm going to add 1 over here on this side. Same thing as, you remember horizontal translation, I would do x minus 1. Well, I'm just adding 1 to both sides there to move it to the right 1 space. Okay? So there is the function that we're dealing with, and now I just need to figure out what I'm integrating it to, okay? Well, now I was integrating it from this point 30, okay? That point 30 is now going to be moved over one to the right, so it's now 40. But because I'm integrating with respect to y, well, all I need is the y coordinate, so that's the 0. All right, so now I know my volume is going to be pi times the integral from 0 to something. Well, now I've got to figure out the y coordinate when 5 is shifted over. Okay. I can actually go back to the original. When x is 5, I've got 25. 19 minus 25 is a negative 16. So multiply both sides by -1, and y squared equals 16, so y is 4. So this point back here was the point 54. So now it's going to be at, of course, 6,4. But again, the y coordinate's what I care about. So it's going to be the integral from 0 to 4. Okay? And now I'm going to be integrating the square root of y squared minus 9 plus 1 squared dy. Alright, so now that's all set up, and that's as far as I needed to go here. Okay? Alright, so our last one here is 1989 AB number 2. It says let R be the region in the first quadrant enclosed by the graph of y equals square root of 6x plus 4, the line y equals 2x, and the y-axis. So we're going to find the area of R. Well, first of all, let's go ahead and graph what this is going to look like. All right. I've got a radical function here that's been shifted to the left 2/3 of a unit because it's 6x plus 4. It's also been shrunken horizontally. But it's basically, it's going to be looking something like this. All right. I also have the line y equals 2x. So that is going to go through the origin. And it's going to go up 2 over 1. All right, now, didn't point this out before, but this, my square root of 6x plus 4, if I plug in 0 for x, I'm going to get square root of 4, which is 2. So this right here is the point 0, 2. That'll be significant here in a moment. Okay, but we have this line going like this. Okay? And they said it's enclosed by these two graphs and the y-axis. All right, so what area are we talking about here? Well, if I look closely, those two and the y-axis enclose this area right here. Okay? Just to clarify, we have this straight line, and we have this. Okay? So that's the area we're talking about. So first of all, we need to find the area of R. All right, so the upper function here is the square root of 6x plus 4. Okay, so if you remember, area is simply the integral from intersection to intersection, or in this case, endpoint, where x is 0, to the intersection point, which we need to find, of the upper function minus the lower function. Okay? And that's going to be dx. Now, I need to find the intersection of this, so let's take a moment and do that. I have square root of 6x plus 4 equals 2x. I'm going to square both sides, so I get 4x squared equals 6x plus 4. I'm going to subtract those to the right-hand side and divide everything by 2. So I'm going to get a 2x squared minus 3x minus 2. That factors into 2x and x, and that's going to be a minus 2 and a plus 1. Okay, so you'll notice here these would intersect at, yeah, minus 4 plus 1. There we go. So at x equals a negative 1/2 and a positive 2. Okay, well, the negative 1/2 got cut off by the y-axis. So really all we care about right here is this point 2, 4. 2, 4. We can double check that. 6 times 2 is 12, plus 4 is 16, square root is 4. So there's our intersection point, and that gives us the upper bound of our integral. So all we need to do at this point is actually do the integration. This one I am going to need to separate, because the first half I'm going to have to use u substitution for. So it's the integral from 0 to 2 of the square root of 6x plus 4. I need a 6 dx. So I'm going to have a 1/6 out here. Okay? And then I'm going to have a minus 2 times the integral from 0 to 2 of x dx. Alright, so there's that second half. Alright, so now that I have the integral of u du, the integral of the square root of u du, the integral of the square root is that to the 3/2 times 2/3. Okay, so I have 1/6 times the 6x plus 4 to the 3/2 power times 2/3. Okay, and that's going to be evaluated from 0 to 2. Minus a 2x evaluated from 0 to 2. Okay, so let's keep going here. We've got 1/6 times, if I plug in a 2, I get 16 to the 3/2. Well, that's the square root of 16, which is 4 cubed, so that's 64 times 2/3. And then I have to subtract this evaluated at 0, which is just going to be 4 to the 3/2, which is 2 cubed, which is 8, times 2 is 16/3. Okay? And then the minus 2x evaluated from 0 to 2 is just going to be a minus 4. Alright, so simplifying here, 2 times 64 is 128 over 3, which 128 over 3 is 42 and 2/3, minus 5 and 1/3, okay, and this is again times 1/6, alright, all minus 4, so that's 37 and a third times 1/6, okay, and maybe I should just left this in terms of thirds. You know what, I'm going to actually do that. Erase here. Okay, so yeah, that'll be a lot easier. 128 minus 16 is going to be 112 thirds. And then it's going to be 112 18ths minus 4 is going to be 72 18ths. Okay. So that takes it down to 40 18ths, which is 2 and 4 18ths, which is 2 and 2 ninths. and that's the area of that region, 2 2/9.